This is the second part of stacks, and really a lot of this chapter, the rest of this chapter, is more on applications that stacks are used a lot in program routines. So there's three major functions that we're going to cover, and I'm probably going to leave a lot of the logic to you. I'll point out some key points. And then the fourth is a well-known problem that, based on who you're interviewing with, they may ask you to discuss a solution for this. So let's just go through some of the applications briefly and go from there. So I'm going to look at three different types of applications. One of them is parsing. How do I parse elements out of a string of data or command structure? How do I postpone an activity being done? And then some algorithms, especially when we get to looking at graphs and trees, sometimes you're going to look at how do I, you ever go down be in a maze and you get to a dead end? What do you have to do? You have to backtrack. Well, now I'm going to look at one aspect of how stacks can be used in developing a backtracking algorithm, just to give you, a solution or a thought process in which how to do it. And then we'll look at a classic problem, the 8 queens problem. So think of a chessboard and you've got 8 queens and you got to position them in such a way that none of them can capture each other. So just thought we'll see what happens here. So we're going to look at reversing data. We're going to look at converting decimal to binary. We'll look at some parsing, postponement, and some backtracking. So this isn't the entire program. I think you got some of it from before. But what we're looking at is now I want to look at a couple of things. One is look at here, you're allocating space for the next item. This is the C program, so that you got the malloc in here. But the process is about the same. Now look at it. What am I doing? I'm checking if the stack is true or not, or full. If it's full, I'm done and I can't go any further because you want to prevent errors from happening. And then you're going to say, hey, it's not full, so go ahead and put one item on the stack. So as I'm going through this loop, putting things into the stack until they're full, so now I got a full stack or exceeded all my numbers. Now I've got to print the numbers in reverse. Now remember what a stack is. Now a stack says I'm stacking plates on a table. I can't get to that first plate on the table until I take the other 10 off. So I keep putting, popping things onto that first plate, and then I got to push those plates off. I'd rather see us being, popping it off. So I'm pushing them on and popping them off. So I'm pushing them on the stack, even though hopefully with plates you're placing them, but you get the idea. I'm pushing them on. Maybe even want to think about it, go to a restaurant, one of those buffet restaurants, and they got the plates in front of the line, and they're on a spring-loaded stack. So what am I doing? I'm pushing new plates onto that stack, and then when I take one off, I am popping one off, and it raises all the other plates up one. So you're looking at now. I'm going to try to print these numbers in reverse. Now think of how the numbers went in. They went 1, 2, 3, 4, 5. So number 5 is the top one. Now I want to print them in reverse order. A stack is perfect for a case where I need to do something, put in information in one way, and then easily print them in reverse order. Think about it. If you had a standard array, how would you do it? I mean, you'd have to go through, you have to fill up the whole array, and then you'd have to you have to figure out how many elements you put in and then back it off. So it could be done either way. But in this case, Now remember also that what is a recursive program? I'm calling myself. So this is, I'm calling pop the item off the stack, returning that, and I'm printing the element. And then of course in this case I'm also freeing that item I've taken off. So I've deleted that element. So I'm going to continue to do that until I have an empty stack. So I'm pushing things on as I'm filling it up, and I'm taking things off. So printing things in a reverse order, fairly straightforward algorithm. Here's just an example of the output. Of course, here I'm just cleaning up the stack because you don't want to leave anything. I'll let you go through this example in the book as far as just seeing the pictures of all of these and how to get done with that. Now, the next number, now, you probably did a lot of this in other classes. You definitely did it if you went to any of the Net 125 classes where I worry about converting decimal to binary. So what am I doing? I've got to create a digit, put it in the stack. So I'm pushing it into the stack, making sure I've got that, and then, getting my next entry. So I'm filling the stack, and now I've got to create the binary number. So what is the binary? Now I've got one, you got to make sure that if the stack is empty, now I got to take the first item off. I take that first element off, and then what I do, I convert that number. So I convert what I want printed. I'm going binary, so I'm getting a 1 or 0 based on what's the module of that number. So if it's an odd number, it's a 1. If it's an even number, it's a 0. So I'm going to go, so I've got this loop. I'm checking if it's empty every single time, popping things off the stack. So you push them on, you loop, you check if it's empty, and you pop off. Now, push here, you probably could have had a check as far as, is the stack full? But either way, just knowing that you want to make sure you do the checks between full and check if it's empty. And then once you're done, make sure you clean it up. Another example is parentheses. Now, you've all used IDEs to help your programming. So what do you got here? I've got what happens when I'm missing a parentheses? They give you an error message, right? Because I got mismatched parentheses. So what do? How does the algorithm, the compiler check for that? Well, one of the ways of doing it is have an algorithm that reads the source program and then parses it to make sure that all the opening and closing parentheses are paired. So one, I'm going to loop until I get more data. And I just want to point out something in your pseudocode is don't assume a programming language and come up with other terms. We're trying to keep it simple because you may have to in the future give this algorithm to someone else to solve that may not know the same level of that language as you do. So pseudocode is make it English style. So you may have to put a few more texts, a few more words in there, but you want to make sure it's something that everybody else can understand. So here, what am I going to do? I'm going to loop while I still got data. I'm going to read a character. Now I'm going to check if it's an opening parenthesis. If it is, I put it on the stack. If it's not, I check if it's a closing parenthesis. If it's not, I'm done. Keep going through the loop, get more data. But if it is a closing parenthesis, now I want to check if the stack is empty, which if it is empty, then what? There's no leading parentheses, so I've got a mismatched closing parentheses. If the stack's not empty, pop the stack, and then continue on. So, and then if it goes all the way through, then hey, I got an opening parentheses that I've gone through the whole stack, pop everything off, and I don't have an opening parentheses. So this parsing algorithm is what your compilers are doing, or the IDE, to kind of say, hey, I got I want to make this parentheses red because I can't find the closing parentheses. So a good use for a stack. This is kind of the program for that. I'm not going to let you go through that at your leisure. The next thing is a backtracking example. Now, backtracking, as you can see, this looks like probably could be a railroad station, train depot, but it's a graph, and each node is numbered. So I got each individual node, and I got decision points along the way, and there's usually weighted values to say, okay, which path do I want to take? But at some time you say, I'm looking for the most expensive or the highest value path. So you're going to write an algorithm and say, okay, I'm going to start with 1, 2, 3, I got a decision. Now I got a choice. Do I take the greater or the lesser number? If you go the 4, then I got another choice. I get to each of these destinations. At some point, you can reach a point and go, oops, I don't have the right value. I don't have, or the highest value. And you have to backtrack. I have to go back to a previous point and go through. Keep going down. So based on what your target is, you may have to, once you reach a dead end, you may have to backtrack, and that's really all I'm doing. I go forward, get to a dead end, I know I'm not at the solution, and I have to go back, try a different solution. Go back, try a different solution until the appropriate one is reached. So we'll kind of process a node like this, but you'll see this a lot in graph theory. So if you get into this in your career, at least you've been exposed to it a little bit. So let's look at what the algorithm could be. Now, we're going to use the infix to postfix. I just want to make sure. Okay. So we're going to try to go through using the backtrack formula here. So I'm going to create the stack. So what am I first doing? I am going to call my create stack, and what's that do? Remember, it initializes all the pointers and allocates a space. Now I'm going to loop through every character in the formula. Now, if the character is in open parentheses, I put it in the stack. If it's not, check if it's a closed parentheses. If it is, pop it off. So now you're seeing, what am I seeing? Here you're seeing the same routine a little bit, a little different look as how to push and pop this algorithm to kind of matching up parentheses in it. I may have got the wrong graphs in the wrong order, but we can go through this and pick it up later. And then now I'm going to loop while the character's not. So I'm going to concatenate all these characters together, because what am I trying to do? I'm trying to make sure there's no syntax errors and put a string to it. So I'm going to concatenate the string to the previous postfix expression, pop the stack, I'll keep looping through those until it reaches a closed character. So I've got check if it's an open. If it's a closed character, you're going to go through this. If it's an operator, so a plus sign, multiplication, whatever, now I'm going to do a test priority to see what's more important. Because remember, there are certain mathematical, there's that execution sequence that certain programming functions need to do. So arithmetic operations have a sequence. So you're going to stack those on. You're going to loop until the stack's not done. And then once your priority is reached, now I can go through, I can concatenate that stack. So now I'm going through, so I'm converting this infix algorithm, adding it to the postfix. So I think I got my algorithms in the wrong sequence, but that's okay. And the code for that, we just bypass all that, and there's your physical example of how that looks. Now, here we've got the postfix, and I'm going to evaluate the expression. So I'm going to take this, and I'm just going to basically go take the postfix, and I'm going to return whatever value. So I've got a valid expression and postfix. Now remember what postfix is. What happens? Where are the arithmetic operators? They're at the end. So I create my stack, I loop. If it's an operator, push on the stack. If it's not, I'm going to keep popping things off until I get to my next character. Then go ahead and calculate operator, operation 1, operator, and operator 2. So I'm going to calculate that value and push it back on. So it's relatively straightforward. I'm going to bypass the algorithm code for that. You can go take a look at that at your earliest convenience. So yes, I did insert stuff in there that I didn't need to. Now, one too many things, so I bypass that part of the lecture. Now I've got this graph. So remember, like I said, I got nodes, and I'm going to worry about backtracking. I'm looking for the longest link here. And as I go through this, I may have to return and try a different path to get through this. I mean, you look at this and go, well, it's fairly logical, right? Mathematically, you can go, well, okay. 1 to 2, 2 to 3. Okay, how do I know I get to this 3, what's my decision point? Is your decision point to go to the lowest number or the highest number? If I'm looking for the highest value, you say, oh, I'm going to go to the highest number, and I'll take that branch. So you do a compare. Take the branch here, I go to 13. I do a compare, and I go, oh, go to 17. Oh, wait a minute. 18, but how many steps did it take me to get there? Because I'm looking for the max number of nodes transverses. So I got, 1, 2, 3, 4, 5, 6, 7. Even though my value is higher, I've got more links here. 1, 2, 3, 4, 5, 6. So you're looking for the one with the most links. 4, 5, 6, 7, 11 could have worked too. But based on what algorithm you use, because you got to make a decision point at key locations and decide which path are you going to take. So, and when you make the wrong mistake or the wrong issue, then you can go ahead and you have to backtrack. So, what I'm going to do is determine the path to the desired goal. And basically, all I'm going to do is I got a graph, and all I'm going to do is print that path. So I've got I've got to create the stack. So I'm allocating the information. I am setting the starting point of my node. So I've got to say, what am I starting for? And on a graph, we said, well, we're starting at node number 1. So what am I doing? I'm going to loop through that until it's null, and not the goal not found. Now the goal probably should have been specified here as to what we're looking for. It says for desired goal, we got the map. There should have been a goal target here where we maybe said, I'm looking for the number 16, maybe. So now I'm going to keep looping through. If the map is the goal, if that pointer is the goal, I'm going to set the not goal found. So that means I found the goal, goal not found. I'm going to set that to false. So which means I don't kind of like the double negative there, but otherwise, if it hasn't reached a goal, I got to push the item on. Now I got to check, is it a branch or not? If it's a branch, now I've got to create another branch, push it in the stack and the loop. Now, and then I keep doing this until I get to the next node. At some point, I'm going to have traversed everything in this path. Now, like I said, there should have been one more element here. But, so advance to the next node. Now, if the stack is empty, that means, hey, I've popped everything off. Nothing there. Now I'm going to print the path. I'm going to check if the stack is empty, and now I'm going to pop each of the different points on and then print that pant point until all the way through. So this algorithm probably should have been written a little clearer from the standpoint of, and this is where when you get to pseudocode, you got to be very specific as to what am I asking for. Yeah, I got to give it a map, but I also got to say, what's my desired goal? But you can see here that I'm using, as I go to each of the nodes, I'm checking, is it a branch point? And I'm going to keep pushing things onto the stack until I get to the point where I've got to the end, and then say, oops, now I got to backtrack. There is no path, so now I got to loop. I got to start, checking. I got to check if I got an empty stack. If not, loop back and then come back up. So just know that stacks can be used to do this. Now, let's look at. We'll give you. Here's an example of 4-queen solution. A queen can go in any of the any of these directions, always on a diagonal or vertical, horizontal. But now, how do I position 4 queens on the board? And this is a 4x4 queen. How can I position each one so that they don't interfere, so that this queen is not going to capture either one of those queens? Okay, and here's another one. Nope, can't capture anybody here. So the trick of this algorithm is to find solutions for the position of those queens. So we're using a stack and using a 1-1. This is just XY coordinates as far as each one. So I'm going to go through looping through each one of these to find that solution to go through this. So here's the algorithm. Now we've changed it to an 8 size. So you could change this board size any one you want, but it's got to be a square board. It can't be 5x7. It's got to be 8x8 or 6x6 or 4x4. So my precondition is my board size is the number, and output is what are the printing the positions of where the queens are located. So as with everything else in our stack, we create it. I set my columns and rows to the starting point. And now I'm going to loop through, we're starting with row 1, up until, unless the board size. So if we had board size being 8, it's going to be between 1 and 8. And then I'm going to go through each of the columns. And as long as it's less than a row, I'm going to increment the column, check if it's not guarded, which means, okay, is somebody going to hit me, going to capture my queen? If not, go ahead and place the queen, push the next one on the stack, increment to go to the next row, restart the columns, and then end your if statement. Now, if at the end of the row and you still don't have a position, I've got to take one item off the stack, one column off, remove that queen off the board, and then continue going back up to check the column. So this is a good example of backtracking where you're seeing I'm putting things on the stack. When I reach a dead end without a solution, I pop one off, I go back around, try it again, and try a different solution. So different types of design for these. I'm not going to go through each one of these routines and see, but I'll let you go through and take a look at the software for this. And like the 8 queens algorithm is it's a well-known and it's a good learning tool. I'd take a look at that algorithm and review it. Now, we're going to talk about the concept of stack frame and its use in writing recursive code. So here we're going to say, remember how you can do, you got a program, but I got your algorithm to what's the power, what's my routine here. So I've got to read the base and expression. So I'm testing if this is a power, and I'm going to double check the algorithm and say, okay, I'm being passed the base and expression. Set the 1, I'm going to loop until it's greater than 0, multiplying the base, decrementing the exponent. So I'm just checking if it's a power or not. And this gives you a rough idea of what we're calling about a stack frame. It's all the calls and returns have to be kept in line, have to be lined up so that we know who's calling who and who gets information on. So I'm calling my stack. I start out with 1, it goes to 2, then it goes to 3, and then on my returns, I go from 3 to 2 to 1. So this sequence of calls is a stack frame. So it's just a concept. Here's some data. If I didn't assign you project 23, and I probably should remove this, but here would have been an example how to find white blocks on that. So give you an idea. Here's a picture of a maze, just so you would have had pictures. Some of the projects I did not give you, but show you what kind of problems can be solved using stacks. And if you're interested, go ahead and try them. Let me know how you did. Hopefully this helps a little bit. And if not, give me a call. Let me know. Give me feedback. I want to make sure these things are getting better, not worse. Talk to you later. Bye-bye.